Alright guys, today we're going to be looking at 5.4, the real number system, and in that we're going to be looking at irrational numbers that have non-repeating decimal expansions, which means we're going to be dealing with radicals and how to use radicals. Okay, so the first time you were introduced into radicals was when you did Pythagorean theorem. So remember Pythagorean theorem we used to find sides of a right triangle. Remember, this is your hypotenuse. These are the two legs. These can be interchanged. So this could be A and this could be a B. It doesn't really matter. But A squared plus B squared equals C squared was your Pythagorean theorem. Okay, so that is the start of today's lesson. Okay, so just 1 second. So remember what an irrational number is. So some square roots that you can't take, like square root of 2, is a non-repeating decimal expansion, which means it's an irrational number. So an irrational number is a number that's not a rational number. That sounds like a does statement, right? And therefore has a non-repeating decimal expansion. That means it goes on and on and on forever. It doesn't repeat and it doesn't end. Okay, this number is an irrational number because it doesn't have a pattern. There is a pattern, but there's not a single block of numbers that keeps repeating from this point on. Then you have other repeating numbers there, so that's just giving you some examples of irrational numbers. Okay, so a number like a square root of x is called a radical. Okay, a number that has a root in it is called a radical. This little symbol is called a radical sign, and the x is called the radicand. All right, so what you need to know about some rules of radicals. If you have two numbers being multiplied under the radical, you can break them apart and put them underneath their own individual radicals. Or if you have a fraction underneath a radical, you can break it apart and put the square root on top and the square root on the bottom, if it is a square root. All right? So, let's move on. Okay, so multiplying and dividing radicals. So if you have this, you can also, remember, break it apart into two separate pieces. Okay, so it just says to rewrite the following. So you can do that. Also, if you have them individually, remember you can write them underneath one great big root. Okay, now remember to simplify radicals. This was really hard for a lot of folks when they were in math 2. Okay, so your little brains just weren't ready at that point, but now we're big kids, we can do this now. So what I'm going to do is take a moment and write down what 1 squared is, what 2 squared is, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, then 64, 81, 100, 121, 144, 169, and 196. Okay, and that takes me all the way up to 14. And if you wanted to, we could even go to 225, and that gets you up to 15. All right. Now, what we can do to simplify radicals. The first thing we're going to do is we're going to multiply these two things together. And that's going to be the square root of 75. Now, what we're going to do is I'm going to come in here and say 75 comes right about here in my list. Now, again, I'm going to be giving you a baby calculator, but I just don't have one of those handy right now. So we're going to see what's the biggest number from here. So we'll start here and work our way up. that will go into 75. So 75 divided by 64. No. 75 divided by 49. No. 75 divided by 36. No. 75 divided by 25. Yes, that works. So we said 25 works. So we can break it down into 25 and 3. And you have to use a number in this list. Okay? And you need to use the biggest number. Now, can we take the square root of either of these numbers? Yes, we can. So we can take the square root of 25. The square root of 25 is 5. You cannot take the square root of 3, so this is our answer, 5 square roots of 3. Okay? Now, when I look at this problem, I look at it and I can reduce this fraction before I start. Reduce fraction first. So what number goes into both 54 and 12? And that'll be 6. 9 times 6, and then 2 times 6. And I use my red pen, so that's why I usually my markout pen. Okay. So we have 9 over 2. Okay, and we're going to be taking the square root of that. Now, remember what the rule says for fractions. You can take the square root of the top number and the square root of the bottom number. Now, the square root of the top number is 3. The square root of the bottom number is 2. This is very, very, very important. You cannot have a square root in the denominator. Okay, cannot have the square root in the denominator. So what you have to do is you multiply the top and the bottom by that square root. Okay, so this gives me 3 square roots of 2, and square root of 2 times square root of 2 is square root of 4. Now that square root of 4 is 2. So this is my answer. That's the math behind it, but I'm going to show you a shortcut. Okay? Move just the square root to the top. Denominator will be what is left times the number under the square root. Okay? Sorry. So if you need to pause that for a minute, feel free. But if I have 3 square root of 2, I'm going to move that square root of the square root of 2 up, and whatever's left, which is a 1, times the number that's under the square root 2. 1 times 2 is 2. and that's the same thing. So that's a little shortcut you can do. Okay. Alrighty. And what we just did, getting the radical out of the denominator, is called rationalizing the denominator. Okay. All right. So here we go. The first thing we're going to do is break this down. So again, if we go to our list, 12 comes right here. 9 does not go into 12, but 4 does. Okay, so this becomes 4 and 3. They're both under square roots. Which one can we take the square root of? We can take the square root of 4. So that this becomes 7 over 2 square roots of 3. Now remember what we said the rule is. You're going to take the square root and move it to the top. Okay? So that that becomes 7 square roots of 3 over what's left times the number under the square root. So that's 2 times 3. So that's going to be 7 square roots of 3 over 6. And that's our answer. Okay, hopefully that's feeling a little easier than it did way back when. Okay, when we add and subtract radicals, in order to be able to add or subtract radicals, all the radicals must have the same radicand. So the number under the square root must be the same. So if this is a 3 and that's a 12, I can fix this so that it will become a 3. But if I can't, let's say this is a 3 and this is a 2, I would not be able to add these two things together. Okay? Now, if I look at this one right here, I cannot break 3 down. So I leave this alone. Over here, I'm going to write my numbers again. 1, 4, 9, 16, 25, 36, 49, and I'm doing it kind of quick, sorry. 49, 64, 81, 100, 121, 144, 169, 196, 225. Okay, so here, 12 comes right here. 9 doesn't go into 12, but 4 does. We have 8. This breaks down into 4 and 3. Okay, now we can simplify this one. The square root of 4 is 2. 8 times 2 is 16. So this is now 16 square roots of 3. Okay? And we have the 5 square roots of 3. So if I have 5 of these plus 16 of these, I have 21 of those. I don't add the square roots of 3 together. So I'm going to put a note here. Don't add square roots of 3. All right, let's see if we can simplify these two square roots. Okay, I'm going to do this one first because I already know this one. This one breaks down using 4 and 3, and some of them you're going to use a lot, so you're going to learn what they're going to become. That's 2 square roots of 3. All right, so 45. Let's see. 45 comes right here. So we go, does 36 go into 45 evenly? No. 25? No. 16? No. 9 does. Okay, so we have 9 times 5 gives me that 45. Which one of these can we simplify? That one. Okay, so that's going to give me 3 square roots of 5. But I look here, can I add these? No, I cannot. So this is as far as I can take that problem. We'll put here, can't add, not like radicans. Okay. Now, we've studied the properties of real numbers. We know about natural numbers. Those are our counting numbers. Whole numbers are our counting numbers and 0. Integers are 0, 1, 2, 3, on and on, and the negative versions of those. Rational numbers is anything that can be written as a fraction or a terminating or repeating decimal. Irrational is non-terminating, non-repeating decimals. Okay. All right. Let's see. So we're going to identify properties. Whoops, forgot to turn it over on the back. So you have properties attached right here. Let's make some notes on those. So if you want to pause this and write these down after I go through them. Commutative property for addition and multiplication, order doesn't matter. Okay, so order doesn't matter. Associative property, grouping doesn't matter in addition and multiplication. Same thing for commutative. 0 is the identity for addition. 1 is the identity for multiplication. What that means is when you say the identity, when I do it, nothing happens. Okay, so when I add 0, nothing happens. When I multiply by 1, nothing happens. Additive inverse are when you add opposites. Multiplicative inverse is when you multiply reciprocals. Okay, and distributive property, you know what that means. So if you want to take a minute and pause this and write this down, we're going to go and identify properties in just a minute. Okay, so pause that, write it down. All right, moving on. So if I say something is an integer, okay, 3 plus 4 is an integer. If I am trying to work something out to tell you that something is true, that's just going to be the closure property. I really didn't go through that one very well. So this is the closure property. And then this one they're adding. So you say closure property for addition. Okay. When I add square root of 2 plus pi, it equals pi plus the square root of 2. What do? They just change the order. When we change the order, that's called commutative property. This is a of addition. Here I'm adding 0. So when I add 0, that is additive identity. Okay. Here, if I look at this, the thing that changed is they move the grouping symbols. So when you talk about grouping symbols, that's going to be associative property. And they're multiplying here, associative property of multiplication. Here, I'm adding opposites. So that's going to be additive inverse. This, I'm multiplying by reciprocals. So this is going to be multiplicative or multiplicative. It depends on however way you want to pronounce that word. Multiplicative inverse. And on this one, they took this and turned it into this. They multiplied the 3 times each piece. So that is distributive property. Okay? Alright. Finding counterexamples. Subtraction is commutative in the set of integers. So the order in which you subtract doesn't matter, is what it's saying. And that's definitely false. So let's do 3 minus 2 equals 1. 2 minus 3 equals negative 1. Okay, that would be a counterexample. Division is associative in the set of real numbers. So let's see. Let's do 2 divided by, and then in parentheses, 4 divided by 2. And then let's work the problem. So that's going to give me 2 divided by 2, because we work in order in parentheses first. That gives me 1. So let's do this one. Open parentheses, 2 divided by 4 divided by 2. So this is 1/2 divided by 2. So we do keep, change, flip. And that's 1/4. And they're not equal. Okay? And then the last one, every rational number has a multiplicative inverse. And this one's kind of tricky. 0 does not have an inverse because it does not have a reciprocal. Because when you put 0 in the denominator, it doesn't exist. Okay, so that one was kind of tricky. The rest of them were kind of easy. You could have just made up numbers and put it in there. All right. And I think, and that's all for today. If you have any questions, please reach out and let me know. And have a great day.